Good day to everyone. My name is Ervin and I am representing the authors of this paper. So I will be presenting our paper titled Deep Learning Feature Extraction for COVID-19 Detection Algorithm using the Computerized Tomography Scan. So coronavirus disease 2019 or COVID-19 is a new virus that has created tremendous global chaos, spreading to practically every country around the world since its first outbreak in Wuhan, China. And as of the 5th October 2021, this virus has infected over 200 million people and caused more than 4 million deaths worldwide. The reverse transcription polymerase chain reaction or RT-PCR test is the gold standard for diagnosing COVID-19 because it provides a more definitive answer to the presence of the virus in the human body. However, the sensitivity of the RT-PCR test is inadequate. False negative diagnosis often occurs where a person with a negative RT-PCR result at initial testing has a positive result in the subsequent test. Hence, the negative RT-PCR test result does not indicate the complete absence of the COVID virus in the body. As a result, medical imaging is commonly used as a complementary modality for COVID-19. And nowadays, CT scan is currently the primary method for radiologists and clinical doctors as a COVID-19 screening tools. This is due to its ability to capture essential characteristics of the COVID-19 infected lungs. However, the COVID-19 diagnosis based on the CT scans require radiology expert, and the enormous number of COVID-19 infected cases had resulted in an insufficient number of radiologists. The motivation for this work is as follows. So there is a need for automated screening of COVID-19 to expedite the screening process. Additionally, the combination of imaging technology and artificial intelligence can potentially improve CT scan analysis for COVID-19 diagnosis and accelerate the screening process with minimum power. Finally, one of the main motivation is because of the excellent reputation of deep learning based approaches in image processing tasks. For this work, 3 convolutional neural network based or CNN based feature extractor has been proposed. They are custom CNN based, ResNet50 based, and a VGG16 based. So custom CNN is constructed from scratch with 5 convolutional layers, whereas the ResNet50 and the VGG16 is a pre-trained model. Pre-trained model is a model that was trained on a large benchmark dataset called the ImageNet, and they have their own train weight. The pre-trained model with its pre-trained weight is then utilized to extract features from the CT images used in this work. The original classifier of ResNet50 and VGG16 is removed, and the convolutional base is used to obtain features of all the CT images used in this work. Now figure 1 shows the feature extraction process details, whereas the figure 2 shows a brief block diagram of the proposed work. From the figure 2, during the pre-processing phase, all the CT images are rescaled to 224 by 224 dimensions. The color channel stays as 3 channels RGB color, and the pixel value are normalized into a range between 0 to 1. This is to achieve a consistency in the dynamic range of the images. Now, during the feature extraction phase, especially during the CNN feature extraction, the image is convolved with different learned kernels using shared weight. Then various filters are applied to the raw data of the input image to learn and extract features. The head of the pre-trained model, which is the classifier, is removed, and the convolutional base is used to obtain the features of all the images from the CT scan images. All features are extracted at the last layer of the convolutional base. For the custom CNN and VGG16, The features will be extracted from the final max pooling layer that has applied a dropout, as this layer produced the best learned features after several convolutions. The feature extracted at the final max pooling layer of the custom CNN networks are at the shape of 11 by 11 by 64 dimensions, whereas the VGG 16 output features are in the shape of 7 by 7 by 512. For ResNet 50, the shape of the features are 7 by 7 by 2048, and these features will be extracted at the activation layer. Figure 3 shows the architecture of the deep learning model with CNN classification. It receives a pre-processed CT scan of a lung as input, and the feature will be extracted through the feature extraction phase as discussed in the previous slide. And the feature vector from each model will then be flattened and will then be classified into the following classes, which is either COVID-19 positive class or COVID-19 negative class. In the classification phase, as shown in this figure 3, 3 fully connected layers were added. The first 2 fully connected, or FC, layers uses the ReLU activation function. A dropout layer with a dropout probability of 0.5 is applied between each fully connected layer to prevent the model from overfitting to the training layer. The last FC layer with the softmax activation function calculates the probability for each of the output classes. Lastly, this probability is matched to a threshold value and output the class with a higher probability value. By default, the deep learning models have a threshold value of 0.5. The dataset used in this work is called the SARS-CoV-2 CT scan dataset. It contains 2,482 CT scan images, belongs to 120 patients. It is a well-balanced dataset with approximately equal amounts of COVID positive and COVID negative class. The images in this dataset are digital scans of printed CT images with no regular image size. The smaller size is 104 by 153 pixels, while the largest image is 484 by 416 pixels. Table 1 shows the dataset distribution used in this work. It consists of training dataset, validation dataset, and finally a testing dataset. And the details of these 3 datasets are shown in this table. All the images in this work are then rescaled into 224 by 224 dimension. This is to match the image size trained in ImageNet, since the VGG 16 and ResNet 50 are used, and 224 by 224 is also a commonly used dimension when related to CNN. And finally, square images are easier to work with in a CNN based algorithm. In the training phase, all the 3 deep learning models were then individually trained using the training dataset, and a validation dataset will then be used to tune all these 3 models. So during the training phase, the number of epoch carried out is 100, and the Adam optimizer's learning rate was set to 0.0004. After tuning the hyperparameters during the training phase, a 10-fold cross-validation was performed on a single dataset that includes images from both the training and validation dataset. The images in the training and validation datasets were all divided into 10 folds. This step aims to obtain the overall performance of the tuned hyperparameters. From the 10-fold cross-validation process, it was found that the average accuracy for the tuned custom CNN, ResNet 50, and VGG 16 are 93.16%, 86.14%, and 95.48% respectively, as shown in the table below. From the table, we can see that the VGG16 gives the best performance. After the 10-fold cross-validation test, the next test that has been carried out is to evaluate the three models on an unseen testing dataset. The figure shown here is the confusion matrix and the ROC figures for the custom CNN. This figure is a confusion matrix for the ResNet 50 and the ROC curve for ResNet 50. And finally, this is a confusion matrix and ROC figures for the VGG16. Table 2 summarizes the performance of the three deep learning model in the classification of COVID-19 positive and COVID-19 negative based on the unseen testing dataset. The classification performance of the tuned custom CNN and VGG16 was excellent, with the area under curve values of 0.956 and 0.975 respectively. Since the predictive power of both models is high, the area under curve of custom CNN and VGG16 are very close, almost close to a value of 1, whereas ResNet on the other hand give the lowest area under curve value with 0.856. It can also be noted that the custom CNN scores the highest sensitivity with 90% sensitivity. This can also be seen that the custom CNN exhibit the highest true negative as shown in the previous figure. However, the VGG16 outperformed the three deep learning models in accuracy and specificity with 92.5% and 97% respectively. On the other hand, the sensitivity, specificity, and accuracy values of ResNet 50 for classification are all relatively lower. In fact, it gives the least values of all the evaluation metrics with 84%, 69%, and 76.5% for sensitivity, specificity, and accuracy respectively. Overall, from this table, it can be concluded that the VGG16 gives the best overall performance when evaluated on an unseen testing dataset. The best performing model from our papers has also been compared to other existing COVID-19 classification model that uses the same dataset. Our paper shows a slightly higher accuracy rate. However, the DenseNet 1-to-1 gives a better sensitivity rate. The sensitivity rate is crucial as it indicates the ability of the model to correctly identify a patient's lung CT that belongs to the patients with COVID-19 positive. It is very crucial to ensure that the diagnostic is as sensitive as possible on the CT scan with COVID-19 to minimize the potential of false negative. A comparison of CT scan-based COVID-19 patient classification algorithm using the three deep learning approaches, custom CNN, ResNet 50, and VGG16 has been carried out. And based on the performance evaluation using the SARS-CoV-2 dataset, it was found that the best deep learning model is the VGG16, yielding 95.48 average accuracy from a 10-fold cross-validation test, and 97%, 97.5%, and 92.5% in specificity, area under curve, and accuracy when evaluated on an unseen testing dataset. However, it was found that the custom CNN gives the best sensitivity rate. For future work, multiple datasets can be considered, as this work has only been evaluated on one dataset, thus limiting the variety of training and testing data for the experiment. Furthermore, the effect of image size as well as the training data selection criteria on the COVID-19 classification performance can also be investigated. That's all from me, and thank you for listening.